In this section, we'll work through finding and calculating cell potentials for an electrochemical cell. Calculating the electric potential of a cell has been simplified by the careful measurement of the standard reduction potential of all possible electrodes. The table of those electrode potentials can then be used to predict the electric potential of a cell comprised of any two electrodes. Electrode potential is the tendency of an electrode to lose or gain electrons. So we have either an oxidation or a reduction potential. By convention, the process is viewed as reduction, and the values are reported as reduction potential. This way, the more negative the value, the less likely reduction will take place at that electrode, and the more likely it will be oxidation. The more positive the value, the more likely reduction will take place at that electrode, and the less likely oxidation will. This parallels their activity in single replacement reactions. By definition, the standard reduction potential for hydrogen in a standard hydrogen electrode is 0 volts. This is our standard that we compare everything else to. Here's what's happening here. We have a platinum electrode. We have hydrogen gas bubbling into the electrode. So you have a standard electrode constructed from a platinum electrode with hydrogen gas bubbling on it, and the surrounding solution is HCl. So we have standard conditions here. So 1 molar HCl, 1 atmosphere pressure of gas. So how is it that now we know the reduction potentials of all the elements, and we can just go look them up in a table and know what they are? So standard reduction potentials are determined by constructing a voltaic cell with one electrode being the standard hydrogen electrode, since we know that by definition the reduction potential for hydrogen is 0. So that would mean that here we're always starting with 0 volts. By measuring the voltage between the electrodes, the standard reduction potential of the unknown electrode is determined. So here is zinc. So whatever the voltage is read across these two electrodes, this would give me the standard reduction potential of zinc. Here are a few common electrode reactions and their potentials. So we have some that are very negative. You can see this sodium, very negative. That means reduction is not very likely to occur, and oxidation is much more likely to occur, which we know is true for sodium, right? It's much more likely to give up or lose the electron. On the other hand, here, if we pick this F2 fluorine gas, highly likely to gain electrons or undergo reduction due to the higher reduction potential, positive reduction potential. When we're solving problems with these standard reduction potentials, they'll generally be given in a table format, and we use the ones we need to solve the problem, but there are books of data out there that just have the standard reduction potentials for all of the elements. The strongest oxidizers, or those elements that are most likely to undergo oxidation, have the most negative reduction potentials and make better anodes. To help you remember that oxidation and anode both start with vowels, or else remember also that mnemonic anox, right? Oxidation occurs at the anode, and then the strongest reducers have the most positive reduction potentials, those that are most likely to undergo reduction. They make better cathodes. Remember, red cat reduction happens at the cathode. Or just remember that reduction and cathode both start with consonants. So here's a table with some values to summarize the oxidizing and reducing agent strength. So the more likely reduction is to occur, reduction occurs by an oxidizing agent. So the more likely reduction is, the stronger the oxidizing agent. The more likely oxidation is to occur, or the more negative the values, the stronger the reducing agents.